Hello and welcome to section 2.1a, quadratic functions. And so I'm going to go through the examples of this section, of this part of the section, so that we can do a little more classwork in class and get our questions answered. If you have questions on any of these examples that I'm doing, please make note of them in your notes and come to class prepared to ask those questions. Otherwise, we assume that you have you know what's going on. So here's what we're going to do. So example 1 says, describe how the graph of each function compares to the parent function x squared. It says then graph them on your calculator. So first thing we're going to do is we'll actually go through and just talk about what's happening here. So since this function is being multiplied by 2/5, then that basically means that when we have the a value between 0 and 1, we end up getting a compression. So this graph should be wider and flatter than x squared. Over here for part B, a description of this would be that it is shifted up, shift up 2, and it should be reflected across the x-axis. And how we know that is that the negative sign is the reflection part, and the shift up 2 is the number that's being added outside of the x squared. When it's outside, it's up or down depending on the sign. And then we have 3x squared here. Again, we have a multiple. The a value is multiplied by x squared, so this is either a stretch or a compression. And since the number is bigger than 1, it is a stretch, so this is going to be a much narrower parabola, and that's basically what we're going to be looking at. And so let's see, this guy would be flipped over like that. And then the last one down here has two things happening to it. And so we just talked about this in part B, that we are shifting it up 2. Well, this one is shift down 3 because of the negative 3 here. And then the other value here of negative 4, we always go the opposite direction, so this is shift to the positive side, which is right, 4 units. And so the graph should be, if this was the original at 0, 0, it's going to be down here, shifted down at over 4 units. So it should look something like that. So let's go through and actually graph these. And so to see what they look like and see how close we were. So if I go to my graph and put in x squared as my parent function, and then I'm going to go ahead and graph the first one we were given, and that was 2/5. And when we graph them, you can see that the second graph is wider than the first graph. So that's the 2/5 one, and that's really what we were talking about. So there's that graph. And then, well, I'm going to go back and graph the next one. And this one says it should be shifted up 2 and flipped over. So we'll see if that happens here. And when we graph them, there's the original, and there it's shifted up 2, and it's flipped over. That's our second one. And then our third one says we're multiplying by 3, and we predicted that multiplying by 3 would make the graph narrower than the original one. So let's graph it. And when we do that, you can see that the original one is still on the outside. This one is narrower than the original. And then the last one that we are shifting down 3 and to the right 4. So we'll see if we can do that with the next one. And so when I graph that, you can see that I was shifted over 4 and down 3, and that's what we get when we graph the final one. So that's what these are the things that we were supposed to be looking at, just to look at the original graph, which is the middle one there. And maybe I should have made them bolder so we could tell, but well, it is what it is. So we're shifting them, and that's what we're talking about. So then we're going to talk about the definition of the quadratic function. And basically, here's our quadratic function: is a squared plus ax squared plus bx plus c when a is not equal to 0, because if a is equal to 0, we lose this term, and it's not a quadratic, it becomes a linear. And so then we need to remember our quadratic formula, and our quadratic formula is used to solve for x values. So find out where we're crossing crossing the x-axis, and that's really what we're using this for. So make sure you have this down if you don't remember it. Maybe somebody in the class will sing the song for you. Standard quadratic form is this right here, and this is the way we like to write quadratics when we're sketching graphs. The vertex being h and k. And so that's what we're trying to do. And in order to go from our general quadratic form up here, the definition of a quadratic function, we have to kind of complete the square to go ahead and get it in this form. But luckily for us in our two examples, that to find our vertex and our line of symmetry, we are basically we already have them in we already have them in the vertex form, so this will make things much easier for us. So for vertex form, remember they said right here that the vertex is h and k. Well, h is on the inside, and if you look at it, it says negative h. And if I have a negative h, well, here I have a positive 5. So if it's supposed to be negative h in there, and it's a positive 5, then I needed to change the sign on the negative h, which means that originally I put in a negative 5. So the vertex for this, this is the opposite of what we see on the inside, and this is where we're talking about shifting left and right, and the opposite of what we see. So on the inside, it's the opposite of what we see, and on the outside, it's exactly what we see because it's a positive k. So we see a negative 2, so the vertex is at negative 5, negative 2. And then if we're asked for the line of symmetry, this is basically, the line of symmetry is the x value, because we need a graph. So if we had this graph doing whatever it does, we'll just draw a parabola that looks like this, and my line of symmetry is a line that's going to go down the middle and cut this graph in half. Well, look what kind of line it is. It's a vertical line. So in order to get the vertical line for a line of symmetry, we have to think of the equation of a vertical line, and the equation of the vertical line is usually x equals. And so that's what we're looking for, and the line of symmetry just comes up from what is the x value when in our vertex, and that would be our negative 5. So our line of symmetry is x equals negative 5 would be the line of symmetry for our graph here. And so then in our next one, even though we are flipping this thing over and scrunching it because of this negative 1/2 out front, it really doesn't change where our vertex is. So we follow our vertex and form from up above. We look at our h value, the number inside. The number inside is negative 3. Since it matches the negative h, that means we get a positive 3 for my x. And then outside is a positive 1, so I get a positive 1 for my vertex value. So that's basically what we're looking at for vertex. And then hopefully you can remember how we find our line of symmetry. And if you don't remember, well, we just talked about it over here. Our line of symmetry comes from the x value of our vertex, and so our x value of our vertex is 3, and that would get us our line of symmetry for this graph. And so hopefully we'll have them in vertex form. If not, we'll work on that, and we'll talk about that in the future. So let's move on to example 3 and 4. Okay, so now it says we're going to write these in vertex form. And in order to get them into vertex form, we have to do a little bit of work on this. And this is where the fun begins. So we have to remember completing the square. That's what we're talking about when we deal with these. So in order to rewrite it in vertex form, and then we can easily identify the vertex and the line of symmetry once we get those, just like we did in the previous example. So to talk about completing the square in this case, we only worry about the first two terms, the x terms, when we're dealing with completing the square. And luckily for us, for this first example, there's no value in front of our x squared that we have to deal with. So this makes it a little bit easier for us. So the first thing I'm going to do is I am going to take the middle term and divide by 2. And when I divide by 2, well, this will give me the value, negative 1. So my b value is negative 1. And if I square it, that's the number that I add on. So I add on 1. So when I go ahead and complete the square, I'm going to add on 1. But then I have to remember this is negative 5 comes from the negative 5 that was sitting out here. And then if I add 1, but I don't want to change the problem any, so I also have to subtract 1. So this is the terms I want to deal with. This is going to be a perfect square. And so dealing with this as a perfect square, well, this is something that factors, and the reason we're calling it a perfect square is because when it factors, it'll factor into a squared binomial. So I have x squared minus 2x plus 1, and you can go ahead and factor it, and when you factor it, you should get x minus 1 squared. Well, this minus 1 always comes from the middle term divided by 2. So whatever you get for the middle term divided by 2 will be the number that goes here. So that might be, you can go ahead and factor it. You'll get to the same spot as what I'm talking about if you don't understand what I'm saying. But to get my final function, then, if I combine my -5 and -1, I'll get -6 there. And so now you can see I have this thing in vertex form. And so in vertex form, I can say, oh, well, now I can say my vertex is the opposite of what I see on the inside for my x and exactly what I see on the outside for my y. So there's my vertex, and then axis of symmetry, or line of symmetry, is my x value in my vertex, and so that would be x equals 1. So continuing on with completing the square, well, it's a little bit different as soon as we have this number in front of x squared. You'll notice that it didn't take us very much to do the first one. But so when we have a number in front of our x squared, the first thing we need to do is factor that out of our x terms. So the first thing, I'm going to write this as 2, and then I have x squared plus 4x, and I'm going to leave the 7 alone over here. I'm just going to kind of not deal with it for the time being. And so what it's going to happen here is, again, just like before, when we complete the square, we take our middle term and divide it by 2, and then we square it, and that's the number that we add on. So I'm going to take 4 and divide it by 2, which gives me 2, and when I square that, I get a 4. So I add on a 4 inside my parentheses there. So there's my perfect square trinomial, and then I want to subtract 4 out here to keep the equation in balance, but is this 4 really a 4? Well, if I took this 2 times the 4, it would really be an 8. So I needed to keep track of anything that's being multiplied outside, and so that 4 that I'm subtracting outside really needs to be an 8, which would be the -4 times 2. So that's where I'm getting this -2 from, is because I multiplied this 4 that I put in black here times 2. I'm going to at some point in time. And then this guy over here needs to be multiplied by 2 to keep it in balance. So I need to add 8 and subtract 8 to keep this equation in balance. So as I continue on then, if I go ahead and factor inside the parentheses, well, I should get x plus 2 squared. And then outside, since this was an 8, I have 7 minus 8. I now have my vertex form. And so the vertex of this is the opposite of what I see on the inside, -2, and exactly what I see on the outside, which is 1. And so then my axis of symmetry, or my line of symmetry, is going to be x equals -2. It's the same as what we see when we're dealing with our vertex. It's the same thing we've been doing. So finally, then we get this last example here where we have our we want to write it in standard form. So we want to write our equation as f of x equals a times x minus h squared plus k. That's standard vertex form of a parabola. We're given the vertex of 1, 2, and we're given a point 3, -6. So what we end up doing with this is we do a lot of substitution. We know that our h is 1 and our k is 2, so I can start by doing that. So I'm going to say f of x equals a times x minus 1 squared plus k, which is 2. So there we go. So I've substituted in my vertex. And then you need to understand that we're trying to find out what a is to get the rest of the equation, because the x and the f of x will stay as part of my equation. I already have my vertex, so this a value is the concern. So, but I have these too many variables. I still have a y, an a, and an x that I got to deal with. But the cool thing for us is that they gave us an ordered pair, which is an x and a y. So I'm going to plug these guys in and do a little bit more simplification. So my y is -6. My a value is still unknown. 3 is x minus 1 squared plus 2. So if I go ahead and simplify this, I still have -6 equals a times, well, this becomes 4 plus 2. When I subtract 1 and square it, I get 4. So now I just solve algebraically. I'm going to subtract 2 across the equal sign. And so we end up with -8 equals 4a. And then if I divide by 4, my a value is negative 2. So the final equation that they want for me is, remember, I needed to write this, all of this stuff in this form, into this form at the very top. So my final step is to say, oh, well, f of x is going to equal, this a value is negative 2 times x. My h was 1, so I subtract 1 squared, and then I add on my k value. And so this is my final equation that I, oops, it's supposed to be, I put k there. It's supposed to be plus 2. This is my final equation that I get for this, and that's the solution that they want when we write the equation in vertex form. So remember, if you have any questions on any of these examples, please make note of these and come to class and ask so that we can help you with them.